We have already discussed the binary digital modulation system. Different type of modulation system we have discussed, that like FSK, PSK, etc. Now we will consider M-ary digital modulation system or techniques. In binary modulation, generally the parameter may be frequency, phase or amplitude. That parameter changes per bit basis. That means for each bit, say for ASK, if we want to transmit 2 bits, the data, the symbol, the output signal will change by 2 times. Similarly for PSK, if we consider 2 data, then the phase will change twice. That means per bit, the phase of the output signal, modulated signal, will change. So number of bits becomes equal to the number of change in parameters at the output of the modulator, and that is called the symbol. That means that number of times the changes take place at the output signal of the modulator is the symbol. So in binary modulation system, bit rate and symbol rate are the same, because number of bits becomes number of change in parameters. So number of, in other words, we can say bit rate equal to symbol rate. Now we can artificially enhance the spectral efficiency of the digital modulation system by transmitting number of bits in one symbol. So if we consider a M-ary system where m equal to 2 to the power say L, where L is an integer. L may be 1, 2, 3, not 1 means it is a binary. So 2, 3, 4, 5, etc. L equal to. So under this condition, for L equal to 2, m will be 4. For L equal to 3, m will be 8, something like that. So under this case, symbol rate, that means the output changes number of times, change in output, number of times the output changes. That is also called the baud. The baud rate or baud is equal to the bit rate divided by L. R is the bit rate. That means 1 by L into TB. TB is the bit time. So in M-ary digital modulation system, what we do, each symbol at the output of the modulator carries L number of bits. So if we transmit say 10 symbols and say L equal to say 2, then the bit rate effectively we will transmit 2 times of the baud rate number of bits. So if D equal to 10, L equal to 2, then R will be equal to 20. So 20 bits will be transmitted by 10 symbols. So if we increase L, say L equal to 4, that means at a time we will transmit 4 number of bits. Per symbol we will transmit 4 number of bits. Under this condition, for D equal to 10, R will be equal to 40. That means using the same number of symbols, if we increase the value of L from 2 to 4, the number of bits to be transmitted will be enhanced from 20 to 40. From 20 to 40. So more the value of L, higher will be the bit rate. or in other words, if we keep bit rate constant, the symbol rate will be diminished. So that is the biggest advantage of this A-Mary modulation system. So, and that will enhance the spectral efficiency of the modulation scheme. Now, to understand this A-Mary digital modulation scheme, first we will try to understand the quadrature phase shift keying. Quadrature phase shift keying or QPSK. This QPSK is an extension of binary PSK. Obviously, it is an example of A-Mary system where m equal to 2 to the power 2. That means L equal to 2. So for this case, baud rate D equal to R by 2. That means R equal to twice D. So if symbol rate is 10 kilobaud per second, then bit rate will be 20 kilobit per second. So in this way we can estimate. Now in QPSK, one of the four possible signal is transmitted during each signaling interval, with each signal uniquely related to a die bit. What is die bit? If you consider a string of bits like this, then two successive bits are the die bits. That means the symbol will change depending on the value of the die bit, not a single bit, but the value of die bit, 2 bits in succession. So we can represent the 4 possible die bits by transmitting a sinusoidal carrier with one of the 4 possible values, like say AC cos omega ct. Omega c is the carrier, minus say 3 pi by 4 for die bit say 0 0. AC cos omega ct minus pi by 4 for die bit say 1 0. AC cos omega ct plus pi by 4 for die bit say 1 1. AC cos omega ct plus 3 pi by 4 for die bit 0 1, something like this. So a QPSK signal may be represented in this way. So this phase will change depending on the die bit, keeping this amplitude and frequency constant. So for 0 0 symbol, well, we can have different variations of this QPSK. Like instead of taking it as pi by 4, we can take this one as 0. So in that case, if this one is 0 phase, then this one will be 90 degrees, something like that. So the actual value of the phase will be different, but thing is that difference between two successive die bits, or rather two successive symbols, will be 90 degree. So in this case, the phase can be represented as so this one is TB, this one is twice TB. minus 3 pi by 4, this one for die bit 0 0. For this one it will be something like this, minus pi by 4. For this one is plus pi by 4. And for this one is plus 3 pi by 4. TB is the bit time, bit interval. So in this way the phase will vary, and for 2 bits period the phase will be like this. Now if we consider the signal space diagram, say psi1t and psi2t are the two bases. In that case, for this one is pi by 4, so here this one is minus pi by 4, here this one is 3 pi by 4, so this one is here, and this one is minus 3 pi by 4 means here. That means this pi by 4 corresponds to signal 1 1, die bit 1 1. This one is for 1 0 1 0. So this one is say is 1 1, this one is 1 0, this one minus 3 pi by 4 means is 0 0, and this one is for 0 1. And instead of pi by 4, if we take 0, then one point will be here, next point will be here, then here, then here. So in this way we can modify this system. So in general, ST can be written in this way: AC cos omega ct plus phi it, where this phi it is dependent on the die bit value. So this can also be written as ST equal to AC cos omega ct cos phi it minus AC sin phi it sin omega c t. Clearly we have two distinct components of this QPSK. This component is the in phase component, and this one is the quadrature phase. So this is in phase component, this is quadrature component, and using this equation or expression we can design the block diagram for the generation of QPSK signal. So let us try to understand the basic block diagram of the QPSK generator. So first of all, we have the binary signal this binary signal is divided into two parts. With the help of serial to parallel converter. So in upper part and lower part, this upper part will be the in phase and lower part will be the quadrature phase. So we need an oscillator because we have to generate this cos omega ct. So we need an oscillator. Oscillator will generate carrier signal. That carrier signal must be multiplied with the actual bit. It is a basically it is a PSK modulator. In upper part we have a PSK modulator, in lower part we have another PSK modulator. And in PSK modulator we have already seen that it is nothing but the product modulator. So here we have the in phase channel. Now in quadrature component we have to generate sin omega ct, and that is done by changing the phase of the carrier by 90 degree. So here we have sin omega ct. So now we have another product modulator, and that will give us quadrature phase channel. In short form it is called Q channel. And this one is called I channel. So we have I channel and Q channel, the first one and the second one. Then we must have a subtractor. Output of the subtractor will be a QPSK signal. Well, this is oversimplified picture, but this block diagram, I am showing this block diagram so that you can understand it, the basic generation process. So basically we have two PSK modulators. One, for one modulator the carrier is cosine function, for another modulator carrier is sine function, and then they are subtracted to generate the QPSK signal. Now let us consider the detection process. So in detector we will receive this QPSK signal. Just like PSK, this one must be demodulated with the help of a coherent detector. So we need an oscillator that will generate synchronized carrier So we have a product modulator and then an integrator, conventional synchronous detector. In the lower channel, mind it, quadrature channel or Q channel was modulated by sine function. So this oscillator is generating cosine function, so we have to convert it into sine function. So we need a 90-degree phase shifter. So this 90-degree phase shifter will change the phase of the carrier by 90 degree to produce sinusoidal variation, sine function. Then we have a product modulator. The output will be passed through an integrator. So this one is a correlation receiver. Next we have a decision device. For the I channel and for the Q channel. And we have to provide some threshold voltage for comparison purpose. The output of these two, this is the one PSK signal output, demodulated signal, and this one is another PSK demodulated signal. So we need to produce the actual binary signal. So we have a parallel to serial converter that will produce binary signal. So lower one is the Q channel, upper one is the I channel. Sometimes because of this in phase and quadrature phase component, this type of modulation is also called IQ modulation. Capital I, capital Q, IQ modulation. So we may consider this QPSK scheme as a combination of two binary scheme, that is two PSK, binary PSK, that operate in parallel and employ two carriers in phase quadrature. So PSK is therefore a quadrature carrier multiplexing scheme, a kind of, that gives bandwidth conservation to binary PSK. Now the power spectral density PSD of QPSK can be calculated as sin f ts divided by pi f ts whole square. Here this ts is the symbol time. Symbol time is the ts, equal to 2 TB. TB is the bit duration. So if you plot it, the two-sided spectrum will be something like this. Maximum value is twice s square ts. Now for BPSK signal, if FB is the FB equal to actually 1 by TB. That is the TB is the bit duration. So it is a bit rate kind of. So for BPSK signal, for BPSK, the bandwidth is nearly twice FB. Now for QPSK, the two waveforms form the baseband signal. 1 bit period for both of these signals is equal to twice TB. So the bandwidth of QPSK will be equal to 2 times of 1 by twice TB. That means equal to FB. So for BPSK the bandwidth is twice FB. For QPSK the bandwidth is FB only. That means half of that of the PSK. So that is one of the advancement, or rather advantage, of QPSK over binary PSK, that its bandwidth requirement is half that of the binary PSK. Or in other words, if we keep bandwidth constant, then the bit rate of QPSK will be double that of the BPSK. So this is one of the advantage. So if we jot down this advantage, so for same bit error rate, the bandwidth required for QPSK is reduced to half as compared to BPSK. So bandwidth of QPSK is equal to half of the bandwidth of binary PSK. And because of this reduced bandwidth, the information rate of QPSK is higher. So that is another advantage. The information rate is higher information rate. Also, noise immunity of QPSK is high. Its performance is almost equivalent to binary PSK. So from noise point of view, the performance is identical to that of the PSK. So instead of using PSK, if we use QPSK, we will have extra advantages of this type of advantages.